Hello YouTube. I was cruising through some old files when I unearthed this video that I made something like 5 years ago for a college course. The assignment was to do something a little more on the advanced side with a 3D printer, and I picked designing and casting the handle for a DIY wax sealed die. Now it's a little dry, like I said, I made this for a college class, but I still think a few people on YouTube might find the info useful, so enjoy!
Customized dies. These dies are generally unremarkable and they're fairly easy to make. All I do is face off a brass disc, CAD up a quick design, and engrave the corresponding image. And after a little post-processing, remove the tool marks, the die is ready for service. Now that's where my project starts. My friend will be stamping molten wax with these dies, and she'll need a handle to control the die and keep her fingers safe. I'll design the handle, build a pattern with a 3D printer, and then use that pattern to make a silicone mold for additional production. Along the way, I'll be taking various measurements and attempting to apply a bit of topography optimization. This entire assembly is going to have two main components. There's the grip, which is the bit that the user actually holds, and then there's a collet, which is what actually holds the die. I'll go into detail on how I came up with a final design for both of these components. Let's start with the grip. Let's head over to Fusion 360. This was my first design for the grip, and you can see that it's pretty simple. It is functional, but it's also really bland, and I wanted something smaller with better ergonomics. I also wanted the design to have a definite usage orientation, as I'm going to be applying loads and attempting some shape optimization. The grip design progressed through many iterations. I printed each revision, critiqued it, and then refined the design some more. I spent an embarrassingly long time trying to come up with an ergonomic shape, and I was really shocked when I discovered that the design that I liked the most only had a few CAD operations. I'll share the technique real quickly, maybe it'll be helpful to use someday. All I did was set up a pair of polylines, each representing the extremes of my desired shape. Then I lofted an ellipse between the two polylines, and the result was the handle that I decided to keep for the remainder of the project. For fun, I put these handle designs on my desk at work and asked passing coworkers which they preferred, and the results were actually tough to interpret. Some of my coworkers picked two favorite designs, and others said that they all felt the same. Only about half of the respondents simply chose a handle design that they liked the most. In the end, I just picked my own favorite design and moved on with the project. My employer has a policy that allows employees to use company assets for personal reasons if the usage is properly requested and disclosed ahead of time. I was granted the use of a HandyScan 700, and I used it to compare the CAD design of my handle to the shape that actually came off of my MakerBot. Shifting software, I used Geomagic Control X to generate this heat map. The results confirmed what all of us already know. Parts made on FDM machines, especially consumer-grade machines like mine, shrink. How much? Well, I've never been able to quantify part shrinkage until just now, and the answer is, it depends. The blue regions on this heat map show shrinkage as compared to the original CAD model, while the yellow bits are regions of the part that are sitting proud of the original design. The overall shrinkage is actually smaller than I would have guessed, averaging about 5 thousandths deviation with a max shrinkage of 12 thousandths. On the handle, this is inconsequential. In fact, I scanned the handle primarily out of curiosity. However, the collet on this project is an assembly. Tolerances and shrinkage there will have a huge effect on the success of my project. So let's talk about that next. The design of the collet obviously has to start by knowing how big the object is I'm going to place inside of it. The die, I don't know how well you can read my calipers, is about 1 inch and 780 thousandths. My collet design was inspired by a common tap handle. Threading the collet nut onto this handle results in those beveled surfaces making contact. Additional torque on the nut makes the fingers deflect and the tap stays in the handle. I did the same thing, except my object has a much larger diameter. The die needs to fit inside of the collet, which means that the collet orifice has what's known as a unilateral tolerance. The orifice can be slightly bigger than the die, but if it's too small, then the die simply won't fit. This illustrates one of the nuances of additive manufacturing. As demonstrated with a handle, these parts are going to shrink, so I need to oversize my design accordingly. A perk of having cheap 3D printers is that I don't mind making multiple prototypes, so I made several copies of the collet and eventually settled on a designed orifice diameter of 1 inch and 810 thousandths, which is a full 30 thousandths larger than the die itself. As I did with the handle, I scanned the collet with my employer's HandyScan and then used VX elements to add a best fit cylinder to the collet's orifice. The measurement confirmed that this particular feature had shrunk at least 30 thousandths of an inch. Let's pop into a section view of the collet and talk about thread design for a second. Threads today, at least imperial ones, are described by ASME B1.1. It's an interesting read, and if you're a mechanical engineer, you really owe it to yourself to become familiar with this spec. I'm not going to go over all 192 thrilling pages with you, but I do want to share this diagram. It's the profile of a typical machine thread, and you'll notice that the threads reach their peak via a 60-degree incline. That's a problem for those of us with low-end 3D printers, because any overhang greater than 45 degrees will print poorly. I personally have found that starting with the geometry in B1.1 but modifying that incline to 45 degrees results in functional threads that can print without support, and that's what I did with the threads on this collet. The collet is tightened by a nut, and once again I had to give some significant consideration to shrinkage as I was working through the design. Threads that are exactly inverse to each other will never fit together, so even on traditionally machined threads, there's always a small gap designed between mating surfaces. And the same holds true for my 3D printed threads, except that, owing to shrinkage compensation, my gap ended up being a full 50 thousandths of an inch, which is rather large. The collet design looked great on paper, but I wanted to know if it would actually hold my die securely. I wanted to go past a simple function check and get some hard data. I came up with an experiment, but you'll have to use your imagination a bit to follow along, as my employer would not appreciate me filming myself using company equipment. I mounted the collet onto a torque transducer and applied torque to the nut. The readout of the transducer gave me feedback on how much torque I had applied. Then I removed the assembly from the transducer and dislodged the die. Except I wasn't using a pen, I was using a force gauge, which gave me additional data as feedback. I took 5 readings at each 5 inch-pound torque increment up to a maximum of 20 inch-pounds. The data plotted out to this graph, and I took away a few key observations. First, comfortable hand-tight torque works out to be about 15 inch-pounds, and that's likely the load my friend will apply when she's using the handle. 15 inch-pounds will yield about 10 pounds of retention force, and I think that will be adequate to hold the die in place during normal use. I was also relieved to see that the two variables seem to show a continuous linear relationship. I was worried that I'd find something like the green line on this graph. If true, that would have indicated that the moving parts would lock up at a certain torque threshold and that applying more torque would yield proportionately less holding force on the die. With all that complete, I finally had an idea of what I wanted to produce as my final object for this project. I was very excited when Dr. Joshi suggested that I expand my project with silicone mold casting. It's a fabrication technique that I've never used before, but always wanted to try. I didn't start off by casting my final project. I felt that a trial cast on a simple object would be a beneficial learning experience. Enthusiasm doesn't equal competence, and I knew that I was bound to make some mistakes as I was learning to make silicone castings. I made a frame for a 2-part mold and filled the lower half with modeling clay. Now the clay that I chose was too firm, but I was able to make it work. And incidentally, this 3D printed frame was my second attempt at a container for the mold. My first experiment was made from an acrylic sheet, and it didn't work well at all. I embedded my model into the clay and smoothed out the transition as well as I could. For my first object, I chose to cast a gauge block. Now if you're not familiar with a gauge block, it's a metrology tool that's made to very accurate sizes. Now they're used as standards to calibrate hand tools and reference machine setups, so it makes for an easy mold, but it's also going to make a great reference for me as I try to calculate the shrinkage of my casting material. Then I assembled the frame and filled the remaining volume with Smooth-On's Mold Star 30, that's the blue stuff. The manufacturer's instructions suggested I subject my casting to pressure as it was curing, and I used a repurposed paint can from Harbor Freight as a crude pressure vessel. I don't trust anything sourced from Harbor Freight, so I took the pot outside and gave myself as much standoff distance as I could during the cure. The next morning, I pulled the first half of my mold out of the pressure pot and was quite pleased with the results. The surface finish of my gauge block seemed to be well captured in blue silicone. I set about removing the modeling clay, adding a filling sprue, and refilling the recently vacated volume with fresh silicone. Now, I did spray the first half of the mold with mold release, but apparently I hadn't used enough or I didn't let it cure long enough. Adding another mistake to the pile, the two halves of my mold fused together. But, oh well, that's why we run experiments. I separated the halves with a knife, mixed and poured the resin for my first casting. And here it is, the very first object I've ever cast. I was quite pleased with how it turned out. Actually, I was amazed by the amount of surface finish that the casting captured. So there's my original. You can see there's laser lines from the manufacturer showing the part markings. And those same laser lines I actually captured in the casting. I was extremely impressed. Alright, so now I'm going to figure out how much my casting actually shrank. Zeroing my calipers out of my original, a 4-inch gauge block, and I'm going to put them on top of my casting. It should shrink a little bit. Except it didn't. Look really close at my calipers. It actually expanded a little bit. This is going to be confusing to me, and I'm going to repeat this experiment. If I get the same results going forward, that's the data I'm going to use as I'm calculating how big to make my original for the rest of this project. The data from my gauge block experiment left me a little stuck. I wanted to scale all the 3D printed patterns so that resulting castings would still fit together smoothly. However, the manufacturer of the resin claimed that it ought to shrink about 6 thousandths of an inch per inch, yet my own data showed that the resin somehow seemed to grow. I had to get this straight, so I decided to run another experiment. This time, though, I abandoned the gauge block and decided to cast a 3D printed collet instead. I wouldn't be able to quantify shrinkage, but I'd be able to tell if it would affect my project. If the die still fit into the resulting casting, then I could assure myself that the resin shrinkage would be negligible. I had started making a two-part mold, but I decided that for what I was after, a one-part open-face mold would suffice. After about 4 hours of curing at 60 psi, I successfully replicated my collet. To my relief, the die fit inside of the cast collet just as well as it fit into the 3D printed collet. I could assure myself that the shrinkage factor that I was seeing with the resin was going to have a negligible effect on my project. Having a cast version of my collet allowed me to rerun my torque versus retention experiment. The two materials had different densities, strengths, and coefficient of friction, so there was no guarantee that the cast collet would hold the die as well as the 3D printed one. Hey, now the data is starting to work in my favor. The red line shows the new data, and it appears that the cast collet holds onto the die even better than my 3D printed prototype. Also, having two data series revealed something interesting. Exponential regression lines fit these plots even better than linear ones. This isn't terribly important for my project, but I wonder if the same behavior would be observed on similar applications. For example, holding an end mill in the collet of a milling machine. Having designed the grip and collet separately, I joined the two bodies of my CAD software and sent the job to my 3D printer. I'm just using regular PLA filament. The brand happens to be Inland. I picked it up cheaply from my local micro center. I really wish that I'd been able to pop my print off the build plate and submerge it in silicone. Unfortunately, as we all know, the surface finish of AM parts is quite poor, and I had hours of painting and sanding ahead of me before the part was ready to be cast. For paint, my local Lowe's had some Krylon brand automotive primer that worked well for evening out the small lines between layers. Hand sanding is one of my least favorite shop tasks, and I can't imagine how I must appear to my neighbors while filming myself wearing a respirator. I could have put even more time into preparing the pattern for casting, but eventually I had to cut myself off. It was time to actually make my main mold. As this project is about indirect tooling, I'd like to point out the mold frames that I'm using. Most of the literature that I read about mold making suggested using scrap foam board or acrylic sheets as framing material, but the disadvantage with those materials is that they're typically assembled into box-like shapes that are larger than they have to be. As I'm learning in this project, liquid silicone is expensive, and a custom 3D printed frame that can serve some material easily pays for itself. I'll skip a little footage. I think that by now you get the gist of what I'm doing. The mold wasn't as elegant as I would have liked, but it did work out eventually, and soon after I cast my first handle assembly. I was very pleased with the surface finish. All the hand sanding paid off. If I didn't know myself, I never would have guessed that this was produced off of a 3D printed pattern. Now you can see that some of the resin leaked out, so the part is a little shorter than it ought to be. But the great thing about having a mold is I can put it back together, make a few tweaks, and try again. I wanted to try my hand at generating some lattice structures and reduce the mass of this object. I don't have a 3D printer that can handle small, intricate structures, but I could attempt to make a design. I was able to download a student version of Inspire. It's a pretty big program that does a lot more than shape optimization. Learning to operate it was a little intimidating. I started off by feeding Inspire some simple objects. After a few small victories, I loaded a model of my handle for analysis and optimization. My first inputs were the loading conditions that I expected to place on the handle. I knew from my torque experiment that the working torque on the handle was 15 inch-pounds, and I tripled that for the sake of this analysis. I had to reference some academic literature to find a reasonable value for the force applied by the operator's grip strength. Fortunately, I found this study. The authors were showing a correlation between age and grip strength, but I just wanted to know a maximum value for human grip strength. This allowed me to select 132 pounds force as a maximum working load. Loading the handle properly was problematic. My hand wraps completely around this shape, so the most appropriate scenario is likely an evenly distributed force around the surface of the shape. However, that would mean that there's nothing left to optimize, so I took a little artistic license and decided to model the load as 4-point loads, one for each finger, and then evenly distributed load along the back representing the counter force of the user's palm. Inspire did the rest and gave me some very interesting results. My favorite reduced the volume of the handle by 70%. Not a big deal for a hand tool, but this technology could have major applications in aerospace and aircraft parts. As feedback on Inspire, I was a little disappointed there weren't more lattice generation options. I've seen other programs that allow the user to select the shape of the lattice and specify additional parameters. The software also crashed if I gave it complex inputs, so I had to keep things simple. But this is a fairly new technique, so it's likely that my complaints will be moot after another year or two of progress. I did import my design into NetFab for a what-if scenario. Just look at all those support structures. There's no way I'll attempt to print this, but making the design was entertaining.
Reviewing experiment results is a great way to learn, but don't forget that mistakes are often valuable learning experiences as well. That said, I'm going to spend a few minutes talking about what went wrong on my project in hopes that you'll benefit from my experience. First, have a look at this mutilated collet. A lot of things went wrong here, and I'll start with the weather. My first mold was cured outside in warm weather, and that mold cured just fine. A few weeks later, when I tried to cast my second mold, the temperature dropped. Apparently, I should have paid more attention to the obvious warnings on the silicone's packaging. After the recommended 6-hour cure time, I depressurized my casting vessel and found that the silicone was still runny and tacky. I allowed it to finish curing indoors at atmospheric pressure, and that was a huge mistake. I realized later that all of the gas inside the vessel had been pressurized, and that included the volume inside of my hollow 3D printed pattern. That gas had to go somewhere when I depressurized the vessel, and it leaked out of the pattern and into the gelatinous mold. The mold deformed and then cured into this unusable shape. Lesson learned there. 3D printed casting patterns are hollow. If your casting process uses pressure, you need to account for how that hollow space could affect your casting. Second, notice that this casting is way too flexible. That might have something to do with the curing conditions of the casting, but it's likely more attributed to the ratios of the component chemicals. I deliberately selected a resin that could be mixed by volume, that way I didn't have to buy a measuring scale. In hindsight, despite my best effort, I wasn't able to achieve a perfect 1-to-1 volume ratio, and I wish that I'd just bought a scale and mixed by weight instead. I probably would have gotten better results. In conclusion, I can say that additive manufacturing has huge industry potential as indirect tooling. I'm a proponent of expanding additive So if you're
manufacturing
watching
beyond
this on
simply
YouTube,
protecting the
thanks very much
aerospace.
for sticking
The most
around.
frequent counter
I really
argument
do
I
hope that
receive
something
has to
from my
be,
old
yeah, but
project
we
was
can't use
helpful or
AM to build aircraft
interesting to
parts
you.
yet.
And as always,
And you know what?
comments are
For some
appreciated
trivial,
because,
non-structural exceptions, this is
most of
still
the
a
fun of
valid
having a
argument.
YouTube channel is
However, an
finding and
aircraft part is the
conversing
sum
with
of
other
many
people that
downstream
have the same interest
processes,
as
many
me.
of those include
So
specialized
until the next
tooling.
project,
That
take
tooling,
care and
direct or
thanks again.
indirect,